Hi, Stu Schwartz from MasterMathMentor.com. This is video AB Review 2. The topic is inverses and it covers the AB manual, page 271. No topic in mathematics confuses students more than inverses. If a function, f, is a process that takes x to y, the inverse will be the opposite function that takes y back to x. Perhaps one of the reasons that students get confused is notation. We know that x raised to the negative 1 power is 1 over x, the reciprocal of x. However, f inverse of x, which is written the same way, does not mean 1 over f of x. While x is a number, we can take its reciprocal. But f refers to a process, and there is no such thing as a reciprocal process. With functions, we know that the domain of f is all allowable x values, and the range of f is all allowable y values. Therefore, the domain of f inverse must be the range of f, and the range of f inverse must be the domain of f. We also know that if we start with x and we apply f to it, and then immediately apply f inverse to it, we get x. We start with x, we apply a process, and then apply the reverse process, and we go back to x. So f inverse of f of x is the same as f of f inverse of x, which is x. Let's see this work with typical processes. We know that a function is a process in the form of x, y. So let's suppose that we take x and we add 10. That would then represent the points x, x plus 10. The inverse function is the opposite process, and therefore we subtract 10. So we start with x plus 10, and then we subtract 10, and we get right back to x. The same works with multiplication by 3. Our points will be in the form of x, 3x. The inverse function is dividing by 3. So we take 3x divided by 3 and we get x. Next we look at squaring. We get the points x, x squared. The inverse is square rooting. So we take the square root of x squared and we go back to x. It is important to realize in this example that x must be a positive number, because when we take the square root of x squared, we always get the absolute value of x. And therefore, if x is positive, then the absolute value of x will simply be x. If we take the sign of some number, we get x sine x. If we take the arc sine of sine of x, we go back to x. If we take 10 and raise it to the x power, our points are in the form of x 10 to the x. The opposite to taking 10 to the x is taking the log, and the log of 10 to the x is simply x. We will look at logs in our next video. Finally, e raised to the x power, our points are in the form of x, e to the x. The opposite process, the inverse, is the natural log, and the natural log of e to the x is x. And again, we will see that in the next video. In the first graph, we show f of x in red. F inverse of x in blue is found graphically by reversing all points. For instance, if f of x contains the point 0, -1, then f inverse of x contains the point -1, 0. The graph of f inverse of x will be symmetric to the line y equals x, shown in green. The question comes up whether f inverse of x is a function. There are two ways to determine this. First, we can graph f inverse of x and see if it passes the vertical line test. We can see in this example that it does. Sometimes, though, finding f inverse of x is difficult, if not impossible, much less graph it. However, you can look at f of x and determine if it passes the horizontal line test. If all horizontal lines intersect the graph of f of x in a maximum of only once, then f inverse of x is also a function. In this example, obviously it does. In the second example, we show f of x in red, and f of x is clearly a function. Is f inverse of x a function? We can see that it isn't. We can determine this by graphing f inverse of x, which we show in blue, and it clearly fails the vertical line test. However, it was not necessary to draw f inverse of x. We can just look at f of x and realize that it fails the horizontal line test, and therefore f inverse of x exists, but it is not a function. Finding the inverse of a function is easy. You merely switch x and y. The difficult thing is solving for y. Many times it is not possible to do that, or if it is, it takes quite a bit of work. So, if we have the function y equals 4x plus 5 divided by x minus 1, the inverse is simply x equals 4y plus 5 over y minus 1. In this case, we can solve for y. We cross multiply and get xy minus x is equal to 4y plus 5. Getting all the y's to one side, we get xy minus 4y is equal to x plus 5. Factoring, we get y quantity x minus 4 equals x plus 5, and therefore y is equal to x plus 5 divided by x minus 4. That is the inverse. The graph shows the function y equals 4x plus 5 over x minus 1 in red. It is clear that it is a function as it passes the vertical line test. It also passes the horizontal line test, as wherever we draw a horizontal line, it only intersects the graph at one place. Therefore, the inverse is a function as well. And we can see that as we graph y equals x plus 5 over x minus 4 in blue, and it passes the vertical line test. Note that the two graphs are symmetric to the line y is equal to x. In problems 2a, 2b, and 2c, you are given functions. You are first to find the inverse, and then by graphing, you can determine whether the inverse is a function or not. We interchange x and y and get x is equal to 4y minus 3. Solving for y, we get y is equal to x plus 3 over 4. When graphing the original function, we see that it passes the horizontal line test and therefore the inverse is a function. In 2b, we have y equals x squared plus 1. The inverse, by switching x and y, is x is equal to y squared plus 1, and y squared equals x minus 1. Therefore, y is equal to plus or minus the square root of x minus 1. In graphing the original expression, we see that it fails the horizontal line test, and therefore the inverse is not a function. However, if we restrict the domain of y equals x squared plus 1 to x is greater than or equal to 0, then we will find that the inverse will be y is equal to positive the square root of x minus 1, and therefore the inverse will be a function. In 2c, we have y equals x squared plus 4x plus 4. The inverse is x is equal to y squared plus 4y plus 4, and luckily we can factor that into y plus 2 quantity squared. Therefore, y plus 2 is equal to plus or minus the square root of x, and therefore y is equal to negative 2 plus or minus the square root of x. Again, by looking at the original function, we see that it fails the horizontal line test, and therefore its inverse is not a function, unless we restrict the domain. In problem 3a, b3, and 3c, you are given functions in the form of f of x. You are to find the inverse, f inverse of x, and then show that f of f inverse of x is equal to x. In 3a, we are given f of x equals 7x plus 4. The inverse, therefore, is x equals 7y plus 4. And therefore, solving for y, we get y, which is f inverse of x, is equal to x minus 4 over 7. Looking at f of f inverse of x, we get f of x minus 4 over 7. Therefore, we plug in x minus 4 over 7 for x, and we get 7 times x minus 4 over 7 plus 4. And doing the cancellation, we end up with x. In 3b, we have f of x equals 1 over x minus 1. Therefore, the inverse is x is equal to 1 over y minus 1. Cross multiplying, we get xy minus x is equal to 1, and therefore y, which is f inverse of x, is equal to x plus 1 over x. So looking at f of f inverse of x, we get f of x plus 1 over x. Going to the original f of x, we plug in x plus 1 over x wherever we see an x. And therefore we get 1 over x plus 1 over x minus 1. This is a complex fraction, and we will multiply top and bottom by the LCD, which is x. And therefore we get x over x plus 1 minus x, and we get right back to x. In 3c, we have f of x equals x cubed minus 1. So the inverse is x is equal to y cubed minus 1. And therefore y, which is now f inverse of x, is the cube root of x plus 1. Looking at f of f inverse of x, we get f of the cube root of x plus 1. So we go back to the original statement, and wherever we see an x, we replace it with the cube root of x plus 1. And therefore we get the cube root of x plus 1 cubed minus 1. And that becomes x plus 1 minus 1, and therefore we get x. In number 4, you are given the function f of x is equal to the square root of x plus 2 plus 3. And you are asked to find the domain and range of the inverse function without actually finding the inverse function. For the function, since the square root cannot be negative, x must be greater than or equal to 2. And again, because a square root has its smallest value as 0, the range has to be greater than 3. So the domain of this function is -2 to infinity and 3 to infinity. Therefore, to find the domain and range of the inverse, we just switch the domain and range of the function. Therefore, the domain is 3 to infinity and the range is -2 to infinity. This is verified on the graph. We show the function f of x equals the square root of x plus 2 plus 3 in red. And it is obvious that x must be greater than or equal to -2 and y it must be greater than or equal to 3. The inverse is shown in blue. And we see that the domain is x greater than or equal to 3, and the range is y greater than or equal to -2.